Very good morning to all of you. And in continuation to my previous video on drug model, which was basically the classical model of physics that theorizes the explanation of the experimental results that are obtained for metals, that's consistent, that the theory that we developed in the framework of the drug model could explain us Weidmann-Frey's law. It could explain us the conductivity of these metals, and we assumed the basic postulates of kinetic theory of gases. We utilized those postulates in developing the theory for metals, and we could see that this theory has a good range of explanations as long as the metals are concerned, but at the same time the theory fails when even metal is operating at different temperatures, and it fails to explain the behavior of the solids which are insulators. I mean, an insulator is a material across whom you apply the potential difference, and there is no flow of current. So the theory does not have any explanation for why some of the materials do not respond to the external potential difference. And then there is another class of solids, what we call as semiconductors, and these semiconductors, they do not, their conductivities range between metals and insulators. The drug model has no explanation for those semiconductors, why they conduct the way the semiconductors conduct. So in this video, we'll be focusing on the quantum model that we suffice for the metals, and certainly this quantum model is an improvement over the Drugg's classical model that we have already talked about. So come on now. So the Drugg's model here in this video will be demonstrating, will be incorporating quantum mechanics to redefine to modify basically the implications, the postulates of Drugg's model, and in fact it's not a modification. I believe it's not a modification because the set of foundation for the solver field is the postulates of the quantum mechanics, which is not the case with the Drug model, because Drug model is purely based on classical laws of physics. So what we obtain here, we know that this Drug model explains electrical and thermal properties of metals, but when we use quantum mechanical model, it explains the character, the thermal and electrical properties of materials more accurately, and based on concept of free electrons behaving like quantum gas. And if you rightly go back to the Drug model, we are treating our system which is filled with electrons. We also have an electron gas, but that's a classical electron gas where every electron is treated as a point mass. But here we are treating this what we call as this electron gas is treated as the quantum gas. So the background is the Drug model was given in 1900, electrons as classical particles. We have done that, and it fails to explain the temperature dependence and heat capacity as I was talking about. So certainly there is a need of quantum approach, and this quantum approach was given by Sommerfeld in 1928. So what are the key assumptions of Sommerfeld's model? electrons are free, they are non-interacting. They don't interact with each other. They obey Fermi-Dirac statistics, and we know the Fermi-Dirac statistics is applicable to the situations where we have the system of particles as fermions, and fermions can in general be called the particles which obey in their distribution the Pauli's exclusion principle, which obey the Hund's rule. This system of particles is called as fermions, and the statistics that we use to understand the behavior of fermions is what's called as Fermi-Dirac statistics. So Fermi-Dirac statistics is a basic tool for understanding the electron system of these materials. And what is assumed is that the potential inside the metal is constant. So here we assume that the potential inside the conductor is constant, and at the same time the potential at the surface of the conductor is assumed to be infinite. And so these electrons are confined to these metal volumes where you have a constant potential, and this constant potential can be treated as zero as well, and the surface of the metals can be treated as positions where the potential is extremely infinite. So there are two important definitions that we might encounter when we'll be talking about the quantum field, quantum theory of these metals using Sommerfeld model. The first thing is Fermi energy, and before Fermi energy we have something called as Fermi level, and when we talk about the Fermi level, suppose we have some levels, level 1, level 2, level 3, level 4, level 5. In the context of Pauli's exclusion principle, which tells us that no two electrons can have same set of 4 quantum numbers, or we can say that the two fermions cannot take the same quantum state. So what is possible here in these energy levels is that you can have 2 electrons in each energy levels with spin anti to each other. So you have 2 electrons, 2, 2, 2. So suppose this is the 5th level is the last level. So the level which is last filled level of electrons at absolute zero, this level is called as the Fermi level. And certainly the electrons in that last level, which is filled at absolute zero, they must have some energy. The energy these electrons possess at that level, we call this energy as Fermi energy. So this is what it says: Fermi energy is the highest occupied energy level at absolute zero. So only electrons near Fermi level contribute to the conduction. So the lower level electrons, the levels that I was talking about, their contribution is zero. They don't contribute to the conductivity of these materials. And what contributes is the electrons that are in vicinity of this Fermi level. So certainly this theoretical model is an improvement over the drug model, and it correctly predicts the electrical conductivity behavior. It explains low specific heats at low temperatures, and it accounts for the thermionic emission that we have. When you subject a material to an external energy, there is the emission of the electrons. And this introduces electron degeneracy and the so-called quantum pressure. It certainly has limitations. What it does basically, if you think about a metal having fixed positively charged kernels, the potential of one kernel with respect to another kernel, it cannot be constant. It has to be something like oscillatory. But the Sommerfield model predicts it assumes that the potential is constant that's acted upon these electrons. So this is a problem here. So it ignores this periodic potential from the ionic cores, and it does not explain the band structure, because the band structure certainly tells us, it certainly classifies the materials, especially using Cronin Penny model to differentiate an insulator from semiconductor to a metal. And it certainly fails to account for insulating and semiconducting behavior, which certainly comes as a result of quantum theory when we talk about the Cronin Penny model. So to conclude this introduction, this Sommerfield model is a very key, it's a key step from classical to quantum solid-state physics. It certainly makes a foundation for the band theory that we're going to discuss, and it explains key metallic properties despite having all of these limitations. So now what we should do is let's go with the theory of this Sommerfield model. And as I said, what it does basically, you have electrons, and these electrons have constant potential inside the metal, and on the surface of the metal, the potential of the metal is infinite. So when I think in this framework, I automatically come into the domain and think about the quantum mechanics in vicinity of this model. What I have a particle in a box kind of situation here. I have a particle between infinite potentials. The particle does not have any potential inside, but it has infinite potential at the surface. So I can treat this problem quantum mechanically, and the starting equation that I will have for this problem is the Schrodinger's equation, and I can write down Schrodinger's equation in one dimension, assuming a one-dimensional problem, assuming that the potential at 0 and at some length L is infinite, but the potential between 0 and L is treated as constant or 0. So if I write down the Schrödinger's time-independent equation, it is d2 psi by dx2 plus 2m by h cross square e minus v of x psi is equal to 0. But in our case, what we do is we assume that v of x is 0, so we can boil down the Schrödinger's equation to d2 psi by dx2 plus 2m by h cross square e of psi equals 0. So this is our problem. What we start with one electron in context, but then we have to extend this context to the range of electrons, because you have to include the number density of the electrons. So what you have a situation like this. So you have at x equal to 0, you have at x equal to L, and between x equal to 0, if I put this as A and B, between A and B the potential is 0. So if I write down the equation d2 psi by dx2 plus, if we use k square psi equals 0, and this k square we have chosen equal to 2m by h cross square, where everything has its own usual meaning. M is the mass of the electron, h is the reduced Planck constant, and this k is a constant introduced in the differential equation. And we can immediately write down the solution of this differential equation. And what will be the solution? The solution can be assumed as psi of x is a sine of kx plus b cos of kx. And we can proceed from here. We can use the boundary conditions to our problem. We can use the boundary conditions. So the first boundary condition will be at x equal to 0, psi of x will be 0. So if this is the case, then 0 will be a sine 0 plus b cos 0. But sine 0 is 0, so b cos 0 will be equal to 0, so b will be equal to 0. So the solution that we proposed, this solution will be boiled down to psi of x is a sine k of x. Because the next term that we presumed that does not have any physical implications in our problem, because using the boundary condition, that term has gone equal to 0. Now, we can look for another boundary condition. The first boundary condition was for x equal to 0. We can go for x is equal to L. So for x equal to L, again, at L the potential is infinite, and there is no possibility of psi to exist outside L. So at x equal to L, psi of x is equal to 0. So in this case, what I'll have is psi of x is a sine of k. For x, I'll be using L by, I'll be using L. Okay. But psi of x is 0. It has to be 0. So what I'll be left with is a sine kl is 0. But we understand this a cannot be equal to 0. Because when we chose the solution of the differential equation, we got b equal to 0. A was not equal to 0. So a is not equal to 0. So we know it, that a is not equal to 0. Now if a is not equal to 0, then sine of kl is equal to 0. Now psi of anything is psi of n pi. Sorry, sine of anything is sine of n pi. So what can we do here? We can write down sine of kl is sine of n pi. And the sine and sine can be taken off. So kl is n pi. And this k that we had introduced in the Schrödinger's equation, this k is n pi by l. And what is important here is that this is n is, it's an integral number. It will not start from 0. So for 0, there is no acceptability for k. So n has to be either 1, 2, and so on and so forth. So this is by k. Now if this is by k, I can write down the wave function. And here, I'm not interested in wave function. I'm interested in something more fundamental. Because I am in the domain of the condensed matter. I want to deviate my problem to energy only. I'm not interested in the wave function right now. I'm interested in energy. So if I have calculated k, and k is n pi by l. So what will be k squared? K squared will be n squared pi squared by l squared. But this k squared is 2m by h cross squared. So 2m e by h cross squared will be equal to n squared pi squared by l squared. So we can do the manipulations here, and I can calculate the quantized energies that this electron can have. So E is n square pi square and then h cross square by 2m L square. This is the energy of this one electron. And the energy of this electron is quantized. It will not have all possible energies as was the case in the Dredd model. The electron could have all possible energies that you could think about. But here, what we obtain is that this electron has energies and these energies are quantized. Now, to move from here, so this is my energy and I can think of E equals n square pi square h bar square by 2ml square. Now, what is n? N is basically, it gives us the number of the energy levels. Energy level 1, energy level 2, energy level 3. And thinking in the context of exclusion principle, each energy level is going to take 2 electrons as the partners in each energy level. So if I have n number of electrons, then this n can be taken equal to n divided by 2. Now this n is valid up to what is called as Fermi level. And as I spoke about the Fermi level, it is the level that is achieved by these electrons at absolute zero. The highest level that is achieved by the electrons to the highest level, that level that we have at the top is called as the Fermi level. And if I choose for this as an F, then this NF, because we are talking about these things at absolute zero, this will be equal to n divided by 2. So you can say E is, n square pi square, or you can put F here as well for n to give a symbolic presentation of these integers because they are representing the energy levels. So n square pi square h cross square by 2 square will give me 4, 4 2s are 8, this is 8 ml square. Right. Now let's go back to my equation of energy. So what is my energy? E is n square pi square by L square times h cross square by 2m. Okay, now we want to introduce a new definition, a very useful tool at advanced levels as well, and that is what is called as density of states. Density of states. Now, if I formally define density of states, it is the number of energy levels that exist per unit energy range. And this is what is the formal way of understanding the density of states. So density of states, I would like to symbolize it as D of E. So D of E reflects the density of states, number of energy levels per unit energy range. This is what is called as density of states. And if I have to define this density of states for this one-dimensional problem, I can define it as dN by dE. So this equation is consistent with the definition that I have given. The number of energy levels per unit energy range gives us the measure of the density of the states. So if I look at this equation, I can calculate the density of states. All I have to do is to differentiate this equation with respect to n. So what we are going to do, we're going to differentiate this. So when I differentiate this, in the left hand side I will have dE by dN. In the right hand side, h cross square by 2n will be here, and then pi square will be there, divided by L square will be there. For n square, I will have 2n because the differentiation of n square will give me 2n. So this is dE by dN, but as per the definition, I want dN by dE. You can see this, I think here is 2, this 2 and 2 will cancel. Okay, so to calculate the density of states, I have to take the reciprocal of this equation, because as I have defined the density of states for this one-dimensional problem as dN by dE. So to obtain dN by dE, I will take the reciprocal, I will write the dN by dE. So that's going to be equal to mL square by h bar square pi square times 1 by n. Now, this differential in the left hand side, what it reflects the density of states. So for dN by dE, I can think of d of E. And within the parentheses, within these brackets, I think everything is a constant. So I can say that the density of states is inversely proportional to n. So what we can do here, we can incorporate this result in a graph, and this is your density of states, and this is your n, and you have a reciprocal behavior, and the behavior of the density of the states with respect to n will be like this. So for lower values of n, you can see that the density of states is large. That means the number of energy levels per unit energy range is going to increase if the n decreases. The density of states increase, and vice versa. So this is the relation between the density of states and the number of energy levels that we can think about. Now, what we can do here is, let's go back to this equation and let's try to obtain the result in terms of E. So here, you see, I can calculate this n from this equation. Where is that? From this equation. Okay, n. I want only n. I want only n, and n can be calculated from this equation in terms of E. And everything will go up and down. So what will we get? We will get 2mL square. So 2mL square. This will go up, and E will be here, and pi square h bar square will be in the denominator. Pi square h bar square, and in the right hand side you have n square. So for n square is 2mL square by pi square h bar square. So what is it? 2mL square by pi square h bar square. mL square by pi square h bar square. Okay, so this is the value of n square. But in my equation I have only n, so it will be the square root of that. So dn by de. So I can write down here dn by de will be equal to mL square h bar square pi square. mL square by h bar square pi square. And this is for the n. For the n, it has to be under root. And this has to exist here. This is under root of 2m L square by pi square h bar square. I would like to get it out. Under root of e. So you can boil down these constants. I'm not interested in that. What I obtain here is I obtain this dependence of the density of states. That's dn by de. We can see that dn by de is inversely proportional to 1 by under root of e. Now, what does it mean? It means the same thing. You can have a little more steepness. You can have a little more steepness in your graph. Maybe I cannot draw it exactly. And it has to go